This video is another in the series for Math 1133 for UTSA. Today we're talking about 13.5, the Fundamental Theorem of Calculus. So I'm going to do just an overview of the underlying concept of the theorem, and then we'll do some examples of applying it. So in the previous video, we dealt with finding the area under a function using rectangles a little bit, and then we looked at having a computer do a calculation for us. And I said that there's a formula essentially that we can use instead of doing this with rectangles. So here I've got, on the right, I've got the graph of y equals x, and we're going to look at what is the area under that graph, between the graph and the x-axis, in other words, on the interval 0 to b. B could be whatever number, 2, 3, 10, 1,000, whatever. Well, this is a triangle over here, right? So the area is going to be base times height over 2. And since the slope of this line is 1, the rise over run would be 1, that means that the base is b, whatever that is, and the height is b, whatever that is. So the area, that's going to be base times height over 2, or 1/2 times the base times the height, which are both b in this case, right? So basically, the definite integral, which is the area from 0 to b of x dx, this equals b squared over 2. That's just a formula, okay? Now, where does this come from? Well, the triangle, but another way to look at it is this. If we ignore the triangle temporarily and think about what is the antiderivative of x? Well, use the power rule, you get x squared over 2. If you then plug in the endpoint, you get b squared over 2, okay? So the antiderivative essentially gives you the area. How about if we look at a similar example, related example? What is the area under y equals x on the interval a to b? So now this is a trapezoid. This is the situation we had before, right? And we talked about how if you say, oh, well, I'll just cut this here and I have an area of a triangle and I have an area of a rectangle, there's another way to do this. What if I say I have a big triangle, right? And that's going to be area b squared over 2, right? And I'm going to chop off this small triangle. And since the base of this one is a, the height would also be a, so the area is a squared over 2. So the area of the big triangle is b squared over 2, not the trapezoid, the triangle, the whole thing here, right? And then the area of that chopped out part, that's a squared over 2. So if you subtract these, you get just the trapezoid, okay? So the integral from a to b of x dx, this equals b squared over 2, that's the big triangle, minus a squared over 2, that's the chopped off triangle. In other words, you can take the antiderivative of x squared over 2, first plug in b, and then plug in a and subtract, okay? So this works in general. The antiderivative will be a way to calculate the area. So let's look at this example that we had worked out with rectangles, right? We worked out using geometry. We chopped the trapezoid into pieces, and we got the area was 16, as I recall. And then we did it with rectangles, and we got an estimate as we increased the number of rectangles. But we never actually got 16 without using the triangle, chopping the trapezoid into pieces. We never got 16 without doing that. Well, now what we can do is this. I can say the integral from 1 to 5 of x plus 1 dx, if I first find the antiderivative of this, okay? So typically with an antiderivative, as you may recall, we'll use a capital letter to indicate it. So this is going to be x squared over 2 plus x. And typically we would write plus c. But I don't have to use the general antiderivative. I just need to pick an antiderivative. So I could put plus 0 or plus 1 or plus 15 or whatever I want. That number we choose doesn't matter. And the reason is we end up subtracting anyway. So the 15 would cancel with the other 15 when we subtract. So let's just not bother with that at all. We don't need it because it'll go away anyway. So this is going to equal big F of 5 minus big F of 1. And we're supposed to get 16, right? So this will be 5 squared over 2 minus 1 squared over 2. So we get, what is that, 25 over 2 minus 1 over 2, so 24. 24 over 2. Oh, we didn't get 16. It was 12. Now I remember. It was 12 all along. I'm not just making it up now. I just remembered incorrectly. It actually was 12. You can go check, of course. So we get 12. No geometry, no rectangles. The rectangles are underlying what's happening. The rectangles are the reason that this works. Obviously, we skip that detail. It's super tedious. We don't need to go through all the details, but that's basically it. So now we can find these areas using an antiderivative. And this is basically the reason why we talked about antiderivatives at the beginning of the chapter to begin with, so that when we get to this point, oh, we want an area, use the antiderivative to calculate the area. So what's next? Oh, here we go. Here's the theorem. If f is a continuous function defined on a closed interval from a to b, including the endpoints, and big F is an antiderivative of f, and it, like I said, you could have the antiderivative with a plus 0 or a plus 2 or a plus 15 or whatever, that the plus doesn't matter, so we usually leave it off. In that case, the integral from a to b of little f of x dx equals big F of b minus big F of a, and that just always works as long as, well, continuous. What does that mean? Well, a continuous function, the short version of that is it's one that you can draw with one smooth motion. The graph, you can draw the graph with one smooth motion. You don't have to pick up like your pen or pencil to make more than one part of the graph. That's the short version. That's technically incorrect, but that's the basic concept. All of the examples we're going to be dealing with will be continuous, so we don't have to worry about that too much. So this is the next example we had done. There was this was a marginal cost function, I believe. This was a no, it was a marginal revenue. No, it was a marginal cost function, right? And we had a calculator or computer give us the value. It was something like 24,000, something like that. So what I'm going to do is find the antiderivative of that function. So you know what? Let's FOIL. That'll probably be easiest. So x squared minus 1200x plus 360,000 all over 450. That's not the antiderivative, I've just FOILed. So this is f of x. So big F of x, the antiderivative, well, that's going to be, we'll put the 1 over 450 out in front, just because that'll be more convenient. And in fact, let's do this. Let's do it in the line above as well, just so it looks more consistent. Okay, there you go. So this will be a x cubed over 3 minus 1200 x squared over 2. Run out of room here. Plus 360,000x. Now, obviously, these are really big numbers, so we are going to use a calculator at some point anyway. But we can we can write down what the area is, or the total, the sum rather, and then have the calculator give us a decimal version of the number. So there's our antiderivative. So this guy equals big F of 149 minus big F of 100. And again, as I recall, we got something like 24,000. So this is going to be 1 over 450 times, well, 149 cubed, big number, over 3, minus, this will reduce, 1200 over 2 is 600, so 600 times 149 squared plus 360,000 times 149. Okay, minus, again, running out of horizontal room, 1 over 450 times 100 cubed over 3 minus 600 times 100 squared. Are we going to have enough room? Plus 360,000 times 100. A tight squeeze. Yeah, cool. Okay, so let me grab a calculator, and hopefully I can just type this whole thing in. I'm not super optimistic, but we'll try. And I get 24,600 41.59, which is what we had gotten before. Now, there's actually another way to do this that might be a little bit easier, that would make this problem easier, and then for other problems, it's kind of essential. So let's look at another example. Let's say I wanted to find this integral from 1 to 4 of 1 over x plus 2 dx. So that's the area depicted here on this graph. So I don't have a formula for an antiderivative like this, so I have to use a substitution, right? So I'm going to say my substitution will be u equals x plus 2, so that du equals dx, okay? So I'm going to have the integral from 1 to 4 of, well, 1 over u, doing the replacement, times du, right? But there's actually a problem here. 1 and 4, these are x coordinates. So when I'm doing the integral with respect to x, I'm starting at 1 and I'm ending at 4. When x is 1, u is 3. So this 1 down here is the wrong number to start at for u, okay? So I'm going to get rid of this. This should be 3. Now, for the upper limit, the top number, when x is 4, if I plug that in, u is 6, okay? So this 4 shouldn't be here. This should be a 6 instead. So when I do a change of variable, when I do integration by substitution, I have to switch over the limits of integration. And now I can go forward and find the antiderivative. So the way we had done this before is I'd write down big F separately, but instead I'm just going to do this. I'm going to write in brackets the antiderivative, so ln of the absolute value of u, and I'll put the numbers at the end of the brackets. This is a shortcut method of doing this where I don't have to write as much. I don't have to write big F of u off to the side or big F of x off to the side. So then I'll plug in the two numbers. So ln of, and since 6 and 3 are both positive, I don't need to bother with the absolute value anymore. So ln of 6 minus ln of 3. One of the properties of natural logarithms, or of logarithms in general, it lets me combine these two values. So this is ln. So this is ln of 6 over 3, or in other words, ln of 2. Okay, so this area right there, that's ln of 2 units. Okay, what's next? Oh, right. So substitution formula. So in the online homework, some of the problems will refer to a substitution formula. This is the formula. So basically, this says that when you have some integral from a to b of a composite function, and you also have the derivative of the inside function with the dx. So this is basically the setup of using the chain rule backwards. You can switch out the inside function and just get rid of it by applying it to the endpoints, which is what we did in the previous example. The 1 turned into a 3 and the 4 turned into a 6. That's essentially the same thing. So all I got to do, I don't have to write u equals and du and so forth if I don't want to. I can just identify, well, here's my inside function. Okay, so if I apply that function to the endpoints, 3 and 6, I can now say, oh, well, this is 1 over u du. I don't have to work out that change separately if it's already set up like this. In this example here, du is dx. In other words, you have to have, oh, this is du. And since that was already kind of set up that way, I could just apply this formula. So you can use this formula. It's totally fine. I think it's easier to learn this method and just, oh, I'm going to apply integration by substitution, change the endpoints when I do that, no big deal, versus trying to use this formula because you have to have things set up the right way. But you can use the formula. I just don't think it's the best way to do it. Anyway, what's next? So some definite integral properties. So these are mostly inherited from antiderivatives. If you have a constant, the first property is a constant multiple property. If you have a constant multiplied against a function inside a definite integral, you can move it out in front just like with an antiderivative. If you have a sum or difference of two functions in a definite integral, you can do them separately, just like with an antiderivative. The additivity is not inherited from antiderivatives, but it's pretty straightforward. This says the integral from a to b of some function is equal to the integral from a to c plus the integral from c to b, which might seem totally cryptic, but there's a diagram that basically shows that that's kind of an obvious thing. So here's a to b, and there's some area under the graph, right? If I pick some place c, right, and I call it c, and I want to work out, okay, what's this area, the area from a to c, and then separately, what's this area, the area from c to b. If I then add those two values together, I will get the total area. That's all of this is saying, that you can take an interval, chop it into two pieces, do them separately, and then add afterward, and you'll get the same result. Hopefully that's fairly obvious. Yeah, of course that works. If you take a region, cut it in half or to two pieces, find the areas separately, add them together, you get the area of the whole thing. Hopefully that's pretty clear. Now, why would we want to do that? Well, what if we had an example like this? I want to find the area under the absolute value function on the interval -1 to 1. Now, of course, these are triangles, so I could just go on that basis. I don't need an antiderivative, right? But let's take this take this as an opportunity to use the fundamental theorem. So another way to write f of x equals absolute value of x is the following. And I guess I'll just repeat what I have real quick. The absolute value of x. Well, this equals, you can write this as a piecewise function. This is x whenever x is greater than or equal to 0, when it's already not negative. This is negative x whenever x is negative, right? If you plug in a negative value, you negate that, forcing it to become positive. So this is just another way of writing the absolute value function. And if you look at the graph, well, yeah, when x is negative, here on the left side of the graph, the slope is -1. Over here with x, where x is positive, on the right side of the graph, the slope is +1, right? This is a straight line slope -1, y-intercept 0. This is a straight line slope +1, y-intercept 0. So yeah, so if I want to find the area, then I want the integral from -1 to 1 of the absolute value of x dx, which does work, except I don't have a formula for the antiderivative of absolute value. I don't have a formula for that. But if I rewrite it in two chunks, I can use these instead. So I'll say this will be the integral from -1. Pause the video and think, where am I going to stop the first chunk? The diagram might make it obvious, though. So I'll go from -1 to 0, because that's the place where the two chunks or the two sections meet at the origin of absolute value of x dx plus the integral from 0 to 1 of the absolute value of x dx. Okay. Now, in this case, since I know the input is negative or 0, right, I'm using this version of the formula. So I can replace that with -x. So this is the integral from 0, or rather -1 to 0 of -x dx. And this is the integral from -1 to 0 of -x dx. And this guy, I have an antiderivative for. Just use the power rule. Plus the integral from 0 to 1. So I know I'm using this section of the function. Just replace absolute value of x with just x. No absolute value bars needed, because everything here in this interval is non-negative. And now I can apply the fundamental theorem. I can say, okay, antiderivative of -x is -x squared over 2. So put this in brackets, -x squared over 2. Evaluate at 0 and -1, right? Plus x squared over 2. Evaluate at 0 and 1. Oh, I'm running out of room here. Yeah, that's okay. I think we'll be fine. So this will be, well, -0, right? Minus -1 squared over 2, right? It's a double negative there. Plus 1 squared over 2 minus 0. I am running out of room, so let's reorganize a little bit. Okay, there we go. Now we have plenty of room. Okay, so this equals, well, 0. -1 squared is 1. Negate it to -1. Negate that again to +1. So 1/2. So 0 plus 1/2 plus 1/2 minus 0 equals 1. So the area is 1. And we had to split the integral into two pieces in order to do this. Okay, what's next? All right. The integral from 0 to 1 of x times the square root of x plus 1 dx. There's the graph of that. So we're finding the area of that purple region. So I'm going to have to do a change of variable. So I'll say that u equals x plus 1. So du equals dx. It's relatively simple. And I'm going to have to, this is one we've done before, I'm going to have to replace this with u minus 1. If you take this equation, subtract 1 on both sides, u minus 1 equals x, right? So this will be the integral, and the limits of integration change. 1 to 2, u minus 1 times the square root of u, which I'll write as u to the 1/2 power, du. Okay, so this is the integral from 1 to 2. I'm not ready to do the antiderivative yet. I need to distribute this. So this will be u to the 3/2 power minus u to the 1/2 power du. Okay, so this will be 2/5 u to the 5/2 power minus 2/3 u to the 3/2 power. Evaluate at 1 and 2. And you might think, okay, now we have to switch back to x, right? No, we don't. We just move forward and use numbers 1 and 2. So this will be 2/5 times 2 to the 5/2 power minus 2/3 times 2 to the 3/2 power minus 2/5 times 1 to the 5/2 power, which is just 1, minus 2/3 times 1 to the 3/2 power, which is just 1. And there we go. There's our number. It's kind of messy, but that's what it is. If I want, I could write this as 2/5 times the square root of 32 minus 2/3 times the square root of 8 minus 2/5 plus 2/3 because I have a double negative. So this is kind of a messy number, but that's it. That's the area. And if we wanted to throw this in a calculator, we could get a decimal number. In fact, let's do that. I'm getting approximately 0.64379, which if you think about it, yeah, that looks like, so yeah, this thing is root 2 tall. Unless I made a mistake, this is about root 2 in height. So this is about half of 1 times root 2. So yeah, okay, fine. That seems like it's roughly correct. So if you have the graph of the thing that you're calculating, and you just ballpark the size of it, and you can see, does this number match what I'm expecting? Okay, what's next? All right, similar problem. So this region here, and we could even ballpark how much that is. So if I plug 2 into the function, this will be 4 times the square root of 26. How much is that in the calculator? 4 times the square root 26. I get about 20. And so that's about half of that. So I'm expecting roughly 10. That's my expectation. Okay, so what should my substitution be? Well, I'm going to use v equals x cubed minus 1. So dv equals 3x squared dx. So I need to put the x with the dx, or x squared rather, and borrow a 3. So this equals 1/3 times the integral from 1 to 2 of the square root, or in fact, I'll write this as x cubed minus 1 to the 1/2 power. We're going to have to do that eventually anyway, times 3x squared dx. Now I can do my replacements, and I'll change the limits of integration when I do that. So this is 1/3 times, if I plug 1 into the formula, I get 0. Okay? So 0. If I plug 2 into the formula, I get 7. So put 7 there, times u to the 1/2 power times du. Okay, so this equals 1/3 times, well, 2/3 u to the 3/2 power evaluated at 1 and at 7. I'm going to go ahead and combine these together and make 2/9. So this is 2/9 times 7 to the 3/2 power times 7 to the 3/2 power minus, well, 1. I made a mistake. I probably said it correctly and then wrote it down wrong. That 1 should be a 0. If you plug 1 into the equation, I get 0. So 0. So 2/9 times 7 to the 3/2 power, or if I want, I can write this as 2/9 times the square root of, I believe that's 343. 7 cubed. Yeah, 343. Okay, so what's 2/9 times the square root of 343? I get 4.11, so it's less than I expected, but maybe my ballparking estimate was just incorrect, because I'm pretty sure there's no mistakes here. I don't see any. Okay, what's next? Okay, so total area. So if I wanted the entire area encapsulated by the function, bounded by the function, between it and the x-axis, then I'm not really looking just under the graph, which is what we had been doing. So if I want this area here, and this area, and this area totaled up, I'm going to need 3 integrals. Why is that? Well, if I just do the integral from here to here, what's going to happen is this section here is going to count negatively because the function values are below the x-axis. They're negative. And then this section here is kind of positively. I'm going to get cancellation. Okay, so I need to do them separately and make sure to take the absolute value of this one. Okay, so let's say this is like, oh, and then also this one would be negative as well. So let's say this is like, I don't know, say this is like 2 and 4 and 6, right? So I would need to do, for this one, I need the absolute value of the integral from 0 to 2 of f of x dx. Or if I want, since I know that the integral is going to be negative, I could just negate it if I want to, or put absolute value bars. Either way is fine. And then for this section, I'm going to need to add the integral from 2 to 4 of f of x dx. And then for this section, I'll need to subtract the integral from 4 to 6 of f of x dx. And those three together will give me the total area. So let's see an example of that. So this example says, find the total area between f of x equals x squared and the x-axis on the interval 0 to 2. Okay, so what I need to do is ask, okay, does this cross the x-axis? Because if it doesn't, if it's entirely above the x-axis, well, then I just want the area under it. That's one integral. That's easier. If it does cross the x-axis, does it cross anywhere in the interval? So I need to know that. So I need to know basically what are the x-intercepts. So I'm going to set this equal to 0. Okay, 0 equals x squared minus 1. Well, this does factor. So this is x minus 1 times x plus 1. So 0 equals x minus 1, or 0 equals x plus 1. So I can solve this equation, x equals 1, or x equals negative 1. And yes, x equals 1, this is in the interval. So I have an x-intercept there. So my graph is going to look a little bit like this. I'll just do a rough sketch. It doesn't need to be super accurate. Something like that, okay? So here is 1, where the graph crosses the x-axis. And let's say here's 2. So this section is going to be counted negatively. This section is going to be counted positively. So I need 2 separate integrals. If you didn't have the graph, how would you tell that? Well, what you can do is the following. This is a little bit reminiscent of the first derivative test. I can say, okay, I know that my interval is from 0 to 2, and I know I have an intercept at 1. So I can check the function value somewhere in between to tell whether or not the graph is above or below the axis. So I can look at, say, f of 0.5 to check here, right? So 0.5, 1.5, so this will be 0.5 squared, 0.5 squared minus 1, which is negative if you work that out, right? You'll have 0.25 minus 1 is negative 0.75. So you can go, yeah, this is a negative, right? And then I can look at f of 1.25. And then I can look at f of 1.5. So this will equal 1.5 squared minus 1, which is positive if you work that out. So I know that the graph is below the x-axis here and above the x-axis here, which of course this matches the graph that I sketched out. So that means to get the area, I want the negative of the integral from 0 to 1 of x squared minus 1 dx. And I want to add to that the integral from 1 to 2 of x squared minus 1 dx. Okay, so this equals, I don't have anything else, do I? Yeah, it's the last example. So this equals, well, negative of x cubed over 3 minus x, evaluated at 0 and 1, plus the same antiderivative, because the function is the same in either case, 1 to 2. Okay, so this will be the negative of, well, 1/3 minus 1 minus 0. Okay, that's this guy. Plus 8/3 minus 2 minus 1/3 minus 1. Okay, so I guess I'll just resolve all the parentheses first. So this is negative 1/3 plus 1. I don't need to bother with the 0. Plus 8/3 minus 2 minus 1/3 plus 1. Okay, so I notice that the 1s and the 2 can all cancel. So I will get, well, 8/3 minus 2/3. So I get 6/3, or exactly 2. So 2 is the area between the parabola and the x-axis, and we're making sure to count the part that's below positively by negating it after we calculate it. Anyway, there is that example. So, quick preview of the next section. What if I had something like this? What if I had two functions? Here's f and g. And I wanted to know what's the area between them. Like this area here. How would I find that area? So we're going to do that in the next section, and we'll look at different applications of integrals, of definite integrals, to calculate various things.